So in the last video, we gave some of the theory behind local stability of first-order equations, as well as a criteria for hyperbolic equations. Let's go back through some of it again. So the first thing I mentioned was that was a sort of intuition for why this works. So we gave the intuition for how, using Taylor's theorem, we can give a linear approximation to a nonlinear first-order equation. And to do that, one of the first things we did was we gave this translation lemma, which I'm not going to prove, but I'm going to give some of the intuition for. So if we have some equilibrium x of a first-order equation, that's not necessarily in a convenient place. And what we want to do is we want to shift the entire equation over so that that's actually sitting on, the equilibrium is sitting on 0. And so the way we do that is we just do a change of variables, per usual. You've seen this in your calculus classes. If you do a change of variables, you can set things so that you move things around. So translations are something that we also did in differential equations. And this one here is, in particular, pretty easy to see that it is a valid translation. So we have u sub t plus 1 is equal to x sub t plus 1 minus x bar. So that's just using this definition here, which of course is equal to f of x sub t minus x bar, which is equal to, and that entire thing is equal to f sub u sub t plus x bar. So that's using this again, except by setting x sub t equal to u sub t plus x bar minus f of x bar, which is equal to precisely how we've defined g sub u of t. Okay, so clearly this is just a translation of the other equation. And I'm not going to prove that the stability properties are the same, as that should be pretty clear. Now, when we do that translation, basically what we're saying is we're shifting everything to 0, and then we want to do a linear approximation around it, and so that's basically an entire point of Taylor's theorem. So if we have a second derivative, we're going to use Taylor's theorem with remainder, then you know that f of x is equal to its value at the point you're expanding the Taylor coefficients around, so x bar, plus the first derivative times the distance from that, so because we've centered it around 0, plus f double prime over 2 factorial, oh, that was the wrong button, f double prime over 2 factorial times x minus x bar squared. So this is just Taylor's theorem with remainder, where this xi term here is in this open interval. And if the distance from our equilibrium is small, then it turns out that our linear approximation is good. So you can approximate f of x sub t minus x bar by f prime of x bar times x minus x bar. And if rewriting that just gives us our new difference equation down here. Just a moment, I think. No, ignore that. That's right. So u sub t plus 1 is approximately equal to f prime of x bar times u sub t. And so this is our linear approximation at around the equilibrium x bar. So now, moving on, it turns out that we don't actually need the second derivative. That was just needed because we were using Taylor's theorem here with remainder. And it turns out that we don't actually need f double prime we don't actually generally need it. Sometimes we need it, but we don't actually generally need f double prime for the purposes of doing this linear approximation. That was only just to control the remainder term, and if the remainder term is small, then you don't actually care about it in some sense. And so in theorem 2.1, we prove the asymptotic properties of our first order equation without using the second derivative. We only need a first derivative here. Again, it has to be on some open interval, and we need that x bar is in that interval, and that x bar is a fixed point. So the same setup. Well, in that case, then we can say that it's locally asymptotically stable if you know that the first derivative has magnitude less than 1. And you know it's unstable if it has magnitude greater than 1. And the proof of this is a little bit complicated. I'm not going to go through it all entirely over again, but just I'm going to give some of the vague intuition. The intuition is that if the first derivative has magnitude greater than 1, then what you're doing is you're expanding outward. So each time you apply your f function, you're going a little bit further away from your equilibrium. Or sorry, if it's less than 1, then every time you apply the f function, you're going a little bit closer to 1, and so you're shrinking down. And that's basically what this technical proof using the mean value theorem is saying. So every time the distance from the equilibrium is shrinking down by a little bit. And so eventually you will reach the equilibrium. And so it's locally asymptotically stable. So if you think about it, this is just basically saying that our linear approximation is that it's c times the, at each point you're getting closer by a factor of c. And the proof for the Euler case is basically the same. And the crux of it is that we're just using the same linear approximation, and each time it's c times the distance, and so that slowly gets bigger. And of course, once it gets out of this range in which c is greater than 1, well, then we don't care about it anymore because it's already left our range. Hopefully that made sense. Proofs are a little bit hard to convey, but basically all you're doing is you're saying that if c is less than 1, then you're shrinking, and if c is greater than 1, then you're increasing your distance from your equilibrium. And if you increase your distance too much, you're unstable. If you can continually shrink your distance forever, well, then you're locally asymptotically stable. Okay, so now that we've proven that, we'll note that motivates this definition of hyperbolic versus non-hyperbolic. So this is because theorem 2.1 only applies if f prime of x bar is not equal to 1. When it's equal to 1, then we can't actually use this to say anything. Sometimes it'll increase, sometimes it won't. It's not obvious and requires you looking at the higher derivatives. Because if you think about it, in the linear approximation, nothing's changing. Everything's staying in place. And clearly, that's not always the case. You might have the nonlinear term causing it to move back and forth, just at a much slower rate in either direction. Okay, before we move on to giving examples, we also showed that there's a way to generalize these ideas to periodic solutions. So remember, periodic solutions are ones that go around and come back to where they started from. Now, the other thing that's nice about periodic solutions is instead of considering this the function f, which slowly moves it around, you can consider the function f to the m, which immediately jumps it all the way back around to itself, and so that turns it into a fixed point of f to the m instead. And so that's basically what theorem 2.2 is saying. It's saying that you can apply the same notions of stability to periodic solutions by just considering the function f to the m. And so in this, up here we took, we took f prime of x bar. Here we're taking the derivative of f to the m. Oh, that was the wrong button. The derivative of f to the m. And that has to be less than 1 or greater than 1 for one of our periodic solutions. Now note that this is we only care about this in the context of we only need to show this for one of our periodic solutions and not necessarily all of them. Why is this? Well, it's because it actually turns out that we don't need it to be true for, if it's true for one of them, it's true for all of them. Let's prove that using the chain rule, just so that we remind ourselves of some of our calculus. So let's see, write this as an aside. So by the chain rule, we know that d dx of f to the m of x1 bar is equal to d dx f to the m minus 1 of f of x1 bar times f prime of x1 bar. So this is the chain rule where we're just breaking out the f to the m on one side and f prime, one of our f to the m on one side and all of our other, one of our f's on the other side. Let me write that out, but it's probably a little bit unclear. So this is equal to d dx of the function f to the m minus 1 of f of x1 bar. But then by the chain rule, we can do function composition separately. So this is the same as d dx of, that had to be of the entire thing. So you need to be a little bit careful with notation here. D dx of x1 bar. And so when you apply the chain rule, that gives you f to the m minus 1 of f of x1 bar times f prime of x1 bar. But note that you can repeat this over and over again. So this is also equal to d dx of, let's go ahead and rewrite f of x1 bar as just x2 bar, because of course that's just the next one of our periodic solutions times f prime of f1 bar. And this is equal to, we repeat that, this is equal to f to the m minus 2 of x3 bar times f prime of x1 bar times f prime of x2 bar. And it turns out that if you keep on repeating this process of the chain rule, that's just equal to f prime of x1 bar times f prime of x2 bar times all the way to f prime of xm bar. But of course, that's just equal to d dx of f to the m of xk bar for any k in 1 to m. And so therefore, it really doesn't matter which point we choose, because the derivative is going to be the same for this for each of those points. And so that immediately implies this corollary. Okay, but now let's give a couple examples of this just so that we're all on the same page. We're going to reuse one of the examples from the last set of videos. So this is going to be x sub t plus 1 is equal to a x sub t over b plus x sub t is equal to some f of x sub t. So that's our function, and we have a and b greater than 0. So recall from our last lecture that not the last video, but the previous one, where we were on section 2.2, recall that the equilibria are x bar is equal to 0 and x bar is equal to a minus b. Now we want to see if those equilibria are stable. So, well, we take the first derivative of our x prime function. So f prime of x is equal to, well, bottom times the derivative of the top, so b plus x times a. Well, we'll just note here that f of x is equal to ax over b plus x. Minus the top times the derivative of the bottom, so ax, the derivative of the bottom is just 1, over the bottom squared, b plus x squared, and that's equal to ba over b plus x squared. And now all I have to do is plug in the values for different equilibria. So if f prime of 0, well, that's just equal, you plug in 0 for x, and so the bottom is b squared, top is b, so top is ba, so that's just equal to a over b. So if a is less than b, then 0 is locally asymptotically stable. Asymptotically stable. And if a is greater than b, then 0 is unstable, because the absolute value is greater than 1. And we can do the same thing for our other equilibrium. So f prime of a minus b, if you write that out, it turns out to just be b over a. And if a is less than b, then 0 is unstable, and if A is greater than B, then 0 is locally asymptotically stable. And so that was a relatively simple example. All we did is we showed that you can just test if something is stable by looking at the first derivative at the equilibrium. Which sort of makes sense, right? Because the first derivative controls the linear approximation. Let's see another example, a little bit more complicated. So this is example 2.4 in the Linda-Allen's textbook. So if we let x sub t plus 1 be equal to r minus x sub t squared, which is equal to f of x sub t for r greater than 0. So this is again, a first order nonlinear difference equation. And we want to solve for x equal to r minus x squared to get the equilibria. Well, that's pretty simple. You just rewrite that as x squared minus x squared plus x minus r is equal to 0. And so by the quadratic equation, you have x, I'm going to say plus minus bar for our two solutions, are equal to minus 1 plus or minus the square root of b squared minus 4ac. So that's 1 minus 4r minus negative 4r, so 1 plus 4r over 2. So, and also we know that our function f of x is equal to r minus x squared. So f prime of x is equal to minus 2x. Plus we know that f prime of x minus bar is equal to 1 plus the square root of 1 plus 4r, which is always greater than 1. So x minus bar is always unstable. And we know that f prime of x positive bar, so the positive equilibria from this, is equal to 1 minus the square root of 1 plus 4r. And then so it depends on r. So if r is less than 3/4, then f prime of x plus bar is less than 1. So x plus bar is locally asymptotically stable. And if r is greater than 3/4, then f prime of x plus bar, so that equilibrium, is greater than 1. So x plus bar is unstable. Now in this particular case, we chose this example so that it also has 2 cycles. So this equation also has 2 cycles. So it has periodic solutions. And in order to get those, we need to solve for f squared of x is equal to x. So that implies that x is equal to r minus x squared squared. If we rewrite this out, this gives us 0 is equal to r minus r squared plus 2rx squared minus x to the 4th minus x. And that's equal to 0. That implies that 0 is equal to minus x squared plus x minus r times x squared minus x plus 1 minus r. And these here are just the equilibrium solutions, which are also obviously going to be invariant under applying f twice. But of course, they're not actually 2 cycles because they're just the equilibria. And so we only care about these. And so we get one 2 cycle with 2 different periodic solutions. And again, applying the quadratic formula, that's 1 plus or minus the square root of 4r minus 3 over 2. So these 2 solutions form a 2 cycle. And I will, this is only real when r is greater than 3/4. So we need r to be greater than 3/4 for this to be a real periodic solution. So let's assume that. And one of your exercises for the breakout session is going to be this exercise. So verify that the 2 cycle x1 bar, x2 bar is locally asymptotically stable if R is between 3/4 and 5/4, and unstable if R is greater than 5/4. Yeah. So I will leave off there, I think. As I said, there are some exercises for breakout sessions, and next time we will spend some time and go into the non-hyperbolic case. So you'll notice that in all the cases here, we needed the derivative to be greater than or less than something. When it's actually equal to 1, then you can't say anything using this test, and you have to use more sophisticated, more higher order methods. Thank you very much, and I will see you later.